This is the second webinar on infrastructure and mobility impacts. My name is Maaike Snelder. I'll be chairing this session. I'm Principal Scientist at TNO and Assistant Professor at the TU Delft at the Faculty of Civil Engineering and Transport and Planning. My work focuses on the design and evaluation of future mobility systems. You'll see this picture here with some flowers. And these flowers here are to celebrate that we can share the results of some work packages in the STAD program. I'm involved in the work of the researchers in this program. So I'm responsible for the development of the new mobility model, of which Bachtijar Ashari will present the results. I lead the STAD work package on infrastructure service networks, in which I also supervise Bahman Madadi, he will present also today. And I'm in the supervisory team of Jeroen van der Gun, and he will present as well. So some rules for today. Your microphones and videos are switched off, but we encourage you to ask questions via the chat. And after each presentation, if there's time, we can take 1 or 2 questions. And also during the discussion at the end, there's more than enough room to ask questions. The presentations will be shared later, and this session is also recorded so that others can watch later as well. This is the agenda for today. So I'll start with a brief introduction on the topic, and then we have 3 presentations of 20 minutes each. So, like I said, Bachtijar Ashari will present the work of the new mobility modeler. Then Bahman Madadi will give a presentation on the design and optimization of road networks for automated vehicles. And Jeroen van der Gun will give a presentation on intersection design. And at the end, we have about 20 minutes discussion. So to start with a question to all of you, do you think that congestion at motorways increases or decreases when cooperative automated vehicles hit the market? Important thing is that there are cooperatives, so communicate with each other. And let's say that they have there's a penetration rate of more than 70%, level 4 automation, so you don't have to pay attention anymore when driving on the motorways. Let me see. Start the poll. We're almost halfway with the answers now. Right, so here are the results. Most of you think that there's a decrease, but some also think that there is an increase, and this is exactly what's interesting about this topic. So it's indeed not very easy to answer because there are a lot of uncertainties, and 2 main things that will change is there will be an impact on the capacity. So when vehicles can communicate with each other, most people think that the capacity will increase, but if they can't, they probably decrease. And at the same time, the value of time will decrease. So you can spend your time in a vehicle different, and that will attract more people on the road. So those are 2 contradicting impacts. So it's not straightforward to see what will happen with congestion. And of course, that is very important also for policy making in the end. So yeah, there are actually a lot of questions that you would like to know about the impact of automated driving. Capacity and value of time are 2 of those effects, but it's also important to know what will happen with user preferences or user acceptance. What will happen with the cost per trip, what will happen with parking, and based on that, what will happen with mobility impacts like the modal split, vehicle kilometers driven, congestion, and also some other effects like safety, environment, and economy. And that's why we developed a new mobility modeler to look at these questions, and that's what Bachtijar Ashari will present later. Now, in the face of all these uncertainties, you have to make investment decisions, and that also raises a lot of questions like is it still required to invest in extra capacity, like new lanes or roads, when these automated vehicles hit the market? So you already saw that congestion might increase or decrease, so that impacts your investment decision. And if we invest, on which roads do we then allow the automated vehicles, and where will we facilitate them? So where are we going to invest in the digital infrastructure and the physical infrastructure? And then on top of that, there's a question like when and where should we start? And these are questions that Bahman Madadi will address in his presentation. And then on the urban roads level, so more detailed questions actually on the intersection level is also what will happen there. So what is the impact of automated driving on delays at intersections? And based on that, what's the impact on the travel time? And then more design-related questions like, should we give priority to automated cars, trucks, or buses? So that's possible via dedicated lanes or adjusted green times. All kinds of questions that we would like to have answers to. And hopefully we will hear them in the coming 1.5 or coming hour. So then I would like to give the floor now to Bachtijar Ashari to present his work on the new mobility modeler. Bachtijar has a master in aerospace engineering and is now working 2 years at TNO. And in those 2 years, he learned a lot about traffic and transport. So Bachtijar, the floor is yours.
All right, thank you. Just let me turn on my camera. Should come up. There it goes. Yeah. All right, Maaike, thank you very much for the introduction. So yes, my name is Bachtijar Ashari, and I work at TNO for the past 2 years at the Sustainable Urban Mobility and Safety Department, a colleague of Maaike actually. And along other projects, I've also been working on the new mobility modeler, which is developed by TNO in collaboration with STAD. I will first tell briefly about what the new mobility modeler is, what it can be used for, some motivation for the development, and also a brief timeline and where we are now and how this came to be. Then I'll briefly talk about the model itself, so the process it goes through, kind of interface you have and what you can do with it. And I will finish with the Province of North Holland study results. So the new mobility modeler is a fast and explorative model to investigate the impact of automated driving, connected automated mobility, shared mobility, and certain pricing and parking policy measures. It looks on the impact of these things on mode choice, on vehicle kilometers, congestion, and parking activity, from which you could derive parking revenue. It can calculate many different scenarios quickly because it's such an aggregated model and it's explorative. It's not very precise in the sense that it makes very detailed calculations, but it's very good to review impact mechanisms. So what happens if you change this parameter? What happens then with the other parameter? Does it increase, decrease? Is there some cross effect you didn't expect? And from there on, you can find avenues to pursue further in more detailed models, but this is more an explorative model to see broad strokes and to see large changes. And example questions which you could answer with this are, for example, what the effect is on traffic congestion if a certain percent of the population would start using highly automated vehicles, or how parking price would affect mode usage in an urban region. And the same would have for other pricing policies. So if you would subsidize public transport or would introduce road pricing, how that would impact the model split. The model development started because there are different developments in the mobility world, as you likely know. And of course, policymakers need to react to that. But they don't know yet what the effects would be of these new developments. New developments like sharing, where people don't have their own vehicle anymore, but they use a vehicle they rent from a service, or autonomous vehicles where people don't need to have a license to drive, but they just can sit in a car and the car drives themselves. They will definitely have an impact on how we design our infrastructure or how we design our mobility sector in general. But policymakers are looking for ways to understand what these impacts are. Things like electrification and mobility as a service are definitely also changes which we see, but these are not included yet in the model and will be taken up later on. So the model development started in 2018 together with the STAD project and also for the study of North Holland. And there it focused on the automated driving and sharing modes. And in 2019, this was further improved by improving basically the backend of the model. It was made faster, it was made more extensible, and most important of all, it was linked to urban strategy as a separate module. And urban strategy is a TNO modeling environment where you can connect different models together and feed the result of one model into the other, and then see the whole picture instead of just, for example, traffic. You can then also see the change in traffic as an impact on the environment in terms of noise and emissions. And that's, in the end, that's something we would like to show more often to policymakers, that changes in one area have an effect on multiple areas. And this modeling step brings that a bit closer. And in 2020, we started coupling the new mobility modeler with a network assignment model. And later on, we will do even a multi-user class network assignment where you can distinguish between automated driving cars and regular cars. And this would allow you to see where on the map the effects arise from the scenarios you calculate with this model. And we're also looking how we can integrate work which is done in the STAD program by PhD researchers in the new mobility modeler, such that we can, of course, improve the model, but also showcase their work, which they've been working on for a few years. So the model, well, I've tried to fit it all in one sheet to not spend too much time on it. So it might look a bit convoluted, but it all starts with trips. And these trips are taken from the OFIN, which is a travel schedule or travel journal, which is collected by the CBS, the Central Bureau of Statistics. They approach around 40,000 people yearly and ask them what their travel pattern was for a single day. So there's 40,000 people spread out over a year. They write down every travel movement they made, indicate what kind of mode they used, when they left, how long it took from where to where they went, all these travel characteristics. And the CBS then links that to their personal characteristics like household income, gender, vehicle ownership, that sort of things. And then, of course, anonymizes it and provides it for use by researchers. And we take that data and then extract trips from it, distribute it over road and region types. And that results in a model split based on these trips, of course, and an intensity of, we call them equivalent passenger cars for every road and region type we look at in the model. We have 3 road types and 5 region types at the moment. So it's very aggregated, but it allows us to be fast in that sense. A bit on equivalent passenger car, why we use it. It's just a way to convert all kinds of different modes to a car, because we know the capacity of a road network for cars. It's definitely an assumption and simplification. But you can think of it as just a regular passenger car is one equivalent passenger car, obviously. But say an automated vehicle, which can drive close to other automated vehicles because they can communicate with each other, takes a bit of less space and is actually a 0.9 passenger car unit. So you can actually fit more automated cars on the road. Then we grow the number of trips, and that's really all that is. We look at expected growth per user group. And user groups in this case are based on the vehicle ownership and household income. And we see from literature or from expectations what the amount of travel will be in the future for these user groups. So if it will grow, or if it grow, how much, by which percentage. And then we increase the trips for these user groups. We do the same for region-based growth, because people will move from say, rural regions to an urban region, you expect more movement in urban regions. And that's why we also increased that. It's good to note that nothing else changes there. It's only the number of trips which increases, but everything else, although we simulate the future year 2040, it all stays the same. So people don't age, people don't change their patterns. There is only the number of trips increases. So that's another simplification and assumption there. Then the modeling starts, where we first do a simple destination choice model. It's an elasticity model which looks at the decrease in travel time or the value of time, and then based on that increases the travel distance by a certain percentage. And again, there the origin destinations don't really change, but it's just the distance in between those origin destinations which increases. And the heart of the model is the mode choice model, which is a multinomial logit estimated on OVIN data again. And what that produces is a new model split based on the scenario parameters we feed in and the trips people have to make from step one, actually. This is all fed into a travel time impact calculation, and that is based on the national model system, where we extracted a macroscopic fundamental diagram. It's not a real network per se, but more a combination of road and region types and the capacity for these combinations. And by converting the model split through these PCU, so the passenger car equivalent, you can see what the intensity capacity ratio would be in these road region types, and from there on determine what the travel time would be. And if you feed back that travel time to the mode choice and destination choice, those choices will change a bit. And if you do this iteratively, we do this for 25, 30 times, you find in the end a converged solution where the average network speed doesn't change anymore. And what that would mean is actually that another mode choice would not improve the travel time of a traveler. And that will give you the output, which is basically a growth factor per mode and origin destination pair. Here's an example of the parameters we use for the mode choice attributes. I'm showing it to indicate how we can do in the background of this model. And obviously new modes are not there in the data yet. We have to estimate them somehow, and we can do that by using the cost, value of time, maximum distance, and travel preferences for them. So, for example, we assume that an automated private car is more or less the same as a regular car, but it has a bit of a lower value of time because you can do something else in the vehicle. Similarly, for the automated shared taxi, we assume it's a bit cheaper because it's shared, but it has a maximum distance because we assume that an automated shared taxi will only travel in the region. And you need some extra time to pick up different passengers, so there's an extra time factor involved for that mode. And these attributes will, of course, change in the future. We will find different pilot studies, different papers where we will find different values for these attributes. And the nice thing about this model is that it allows us into the setup to try out different values and see what the bandwidth is, what the effect is, and to do sensitivity analysis like that. What the user sees is an interface like this, where they can try out more simple, I would say, impacts or more simple changes. For example, changes to the parking costs of a parking concept. With respect to a certain reference scenario, you can increase or decrease the parking cost and then let the model recalculate and see what the effect is on the model split and the vehicle kilometers. You can do it for all parking options. You can do it for just one. The interface allows you to pick and choose. Similarly, you can do that with the public transport cost. Again, with the reference scenario here shown in blue, you can change, in this case, decrease the public transport cost and rerun the model and see what the outcome will be in terms of model split. And running the model is in terms of minutes, it happens in 2, maybe 3 minutes to run it fully and show you the results, so you don't need to wait long and you can test out different scenarios quickly. And output, which is actually quite new to us, is not only so graphs and the numbers, but we can actually assign it to the network now, where the new multi-modeler creates a growth factor. You can apply that growth factor to an OD matrix from another calibrated model, which is existing. You can bring that in, apply it, and then you have a new OD matrix, which reflects this calculated scenario. If you assign both of these matrices, you can then create a difference plot as shown here and see where in your where on the map the difference will arise due to the scenario changes you made. If you have any questions about using this model or just more interested in more information, please contact Fieke Beemster, and her contact details will be in this slide for you later on to look at. So on to the North Holland study. We looked at 4 scenarios there, ranging from lower automation, so that's level 3, 4. It's still high for now, but for in the future, there'll be the lower part to higher, so level 5, and no sharing, or so that means that people are not really willing to share vehicles with other users, or high sharing, that people are really willing to sit with other vehicles, with other users in the same vehicle. We used this region type definition. So we looked at the job density, the average short-term parking tariff, and also added some manual zones or points of interest, like Schiphol or the port, to indicate that these are special regions and that travel happens differently. We included the following transport modes. It's good to note that we did not include, unfortunately, the micro modalities like e-scooters or e-bikes. And partially that is because the level of aggregation is really coarse, as you could see in the region plot just before. And these sort of modes would require a bit more detail. And the results you get from that study are as follows. On the x-axis, you see different scenarios. So on the way on the left, you have the reference scenario of 2040, and then level 5 sharing, no sharing, etc. And on the y-axis, you see the model split, so the share of each mode with respect to the total number of trips. And while you see in the reference scenario that there is a lot of car passengers and some active modes like walking and cycling, compared to the level 5 sharing, so when there is high level automation available and people are really willing to share, a lot of the share is taken up by the automated taxi and also a bit of automated shared taxi. And this means that the share of active modes will decrease, so people will walk less and cycle less. Similarly, you see the thing in level 5 no sharing scenario that, well, of course, the shared modes like the automated shared van and the automated shared taxi are not there anymore, but instead people are more often would use their automated private car. We also did a sensitivity analysis with respect to the level 5 sharing scenario. These are the 3 bars here on the right. And we looked at the sensitivity for travelers' preferences, which is reflected through the mode-specific or alternative-specific constant. We looked at the value of time sensitivity and the variable cost of each mode. And you can see that the model is quite sensitive to those, which is an interesting finding because these are exact values we would need to know more about to properly or accurately model this further in the future. Other results you would see are vehicle kilometers and congestion. And interesting here to see is a bit related to the question Maaike posed earlier at the beginning, is that even though you would have less cars in a sharing scenario, you would have more vehicle kilometers. So this graph shows the number of vehicles, vehicle kilometers, and vehicle hours of delay with respect to the index, the reference scenario of 2040, where the index is set at 100. And in level 5 sharing, you see that there is far less cars, but still there are quite some more vehicle kilometers and even more vehicle hours of delay. And if you look at the different scenarios, it's actually a bit of a similar image where you see an increase in vehicle kilometers and congestion because these automated modes are made available. And interesting to see is that this offset even wins from the increased capacity of level 5 vehicles because they can actually communicate with each other and drive closer to each other and take up less space on the road. And even it offsets the wins you get from less number of vehicles on the road because people share those. Well, the next step, of course, would be to look at interventions. What can a policymaker do to change this model shift back to something which would be more favorable for society? And things you can look at are to introduce new parking modes or make them more attractive. You can change the road pricing of certain roads, or you can improve public transport, which would mean that you either reduce the value of time of those, or you would by providing ways of working there, or you would make them cheaper. And this model also allows you to see the impacts of these interventions. Well, wrapping up, I think I'm just in time, is that this model seems to work well to investigate impact mechanisms of shared automated mobility. It can quite easily be extended to include more emerging modes and parking concepts. And the short computation times really allows you to explore different scenarios quickly, to see what the sensitivity is to different parameters, and to assess the impacts of certain interventions. And we can definitely improve in terms of data and stated preference research. Data from stated preference research and pilots, because that would strengthen the basis of these attributes. And integration with a network assignment, as I showed earlier, really opens up possibilities to assess also environmental impacts, because the platform we have can link a traffic assignment easily to emissions and noise pollution, which would make this model a more holistic approach. This brings me to the end of my presentation. Thank you very much for the attention, and I think I'll give the floor back to Maaike.
Thank you very much, Bachtijar. Very nice presentation. In the chat, there are some interesting questions from Simeon Calvert and Marco van Burstede. I suggest that we take one now and address the other one during the discussion session. So if I take the question from Simeon, he says, I presume that as the model is macroscopic, it doesn't take explicit interactions between different types of vehicles into account. Is this correct? And if so, how can it then accurately consider AV interactions which are different from human-driven vehicles?
All right, so thank you for your question, Simeon. If I understand your question correctly, then I mean the AV interactions, we take them into account by assuming that they take up less space on the road. So they interact with each other and communicate in that sense, and then can drive closer together. And when they, for example, are on a road where they cannot do that, where AV is not allowed, they can be driven as conventional vehicles, where they again take up more space on the road. I'm not sure if this answers your question, but I hope it gives a bit more clarity there. But you're right that we cannot take explicit interaction between different types of vehicles, because we convert to passenger car units.
Yeah, thank you. And of course, discussion can follow also later. And I would like to switch to the second presentation. That's a presentation from Bahman Madadi. He has a background in industrial and system engineering, and is doing now his PhD in the STAD program. He will complete his work in the coming months, so yeah, we will be excited to see his work right now. Bahman, the floor is yours now. We'll be switching to Bahman.
Oh, yes. Let me just upload my presentation. Just a second. Okay.
Find the right button.
Yeah, it says it's uploading. Okay, it's here. Yes. Okay. Stop sharing. Yes.
Okay, please go ahead.
Okay. Good afternoon, everybody. I'm Bahman, and I'm a PhD candidate at the Transport and Planning of TU Delft, as Maaike mentioned. I'm the part of the work package 3 of the STAD project, and what I will share with you today is the last piece of my PhD thesis titled Design and Optimization of Road Networks for Automated Vehicles. Okay, let's start. So, oops. Yes. So we expect great benefits from fully automated vehicles, things such as improved safety, traffic efficiency, less environmental impacts, and great comforts. But how about partially automated vehicles and not fully automated vehicles? And how about the transition period until that time where you have a full fleet of fully automated vehicles on the roads? So if you look at the automation levels here, as you can see in the last row, where the operating design domain or ODD of different automation levels are mentioned as, so, yes. As you can see here, all automation levels apart from level 5 have limited operating design domain. So that means they can't use the automated driving system or ADS everywhere on all conditions on the network. And this well raises the question that how and where can we accommodate automated vehicles on road networks during the transition period? Then if we think of different alternatives, of course, we can think of dedicated AV infrastructure. That's one option for accommodating partially automated vehicles on the roads. And the other alternative would be having them on mixed traffic. Then for dedicated AV infrastructure, dedicated AV lanes, dedicated AV links, and dedicated AV zones can be alternatives, and mixed traffic can happen on regular infrastructure as it is now or on enhanced infrastructure. So I will explain all these concepts shortly, but clarify what I mean by enhanced infrastructure. So I want to show you a small result of the work that has been done by a student in our department, and her result was in proceedings of the COTA conference in 2019. So there are different studies specifying different possible infrastructure adjustments for automated vehicles, but I chose this one because it can tell the story very nicely. So what she did was to consider different scenarios based on acceptance of automated vehicles and government support for infrastructure for automated vehicles. And she came up with different scenarios, and I picked two of them. One, just the basic supports, very minimal required infrastructure, and the advanced support, all possible infrastructure support that you can have for automated vehicles. And what she did was to ask and interview quite a lot of experts and try to classify and categorize their opinions and try to come up with this list. So what we see here in the basic infrastructure scenario, we have clear and harmonized lane marking and road signs and galleries and high definition maps and road databases, some basic vehicle to infrastructure communication, and yeah, you can see the different options here. And then for the advanced infrastructure scenario, well, you have the same options, but on top of that, there is the possibility for having a specific type of infrastructure for automated vehicles, such as sensor readable lane markings and road signs, and more advanced cloud centers and road sign units, and different pavement material to adjust to the specific automated vehicles. Now, as I said, there are a lot of different studies in the literature showing different possible infrastructure adjustments, but I'm not going to go into the details of that. The purpose here was to just clarify what we mean by enhanced infrastructure. And then the question rises, do we need this on all roads? So if we want to upgrade all roads in a network with such infrastructure adjustments, especially the advanced infrastructure, we know that these adjustments can be very costly. And also maybe we need them on all roads. So then how do we address this question? So one way to think of the question is to make a selection of roads. This is kind of a vision that we proposed in our previous study, to have an automated vehicle-ready subnetwork, which means to have a selection of roads and the networks where we upgrade them with infrastructure adjustments, and we only allow and facilitate automated driving on this part of the network. So at the network level, it can look like this. So this is just an example on the network of Amsterdam, but you can see the green parts on the network. These can be a selection of roads that are enhanced for automated driving. And yeah, the selection of roads, we had different criteria for selection, but just the main ones were road function and homogeneity of mass and different road types, and the complexity of interactions between automated vehicles and other road users. So we try to minimize this. The idea was to have a selection of roads that are inherently safe, or they can become safe with reasonable infrastructure adjustments, and then try to formulate an optimization problem that maximizes the benefits we can get from enhancing these roads and optimizing the trade-off infrastructure investment cost and the benefits they provide. And then the next concept is having a network of dedicated AV lanes. So this has been proposed by a few different groups of researchers. The general concept is that you can have a dedicated lane. For example, as you can see on the bottom picture, the out left lane can be assigned to automated vehicles just with signs, or as you can see on the top picture, something a bit more clear that this lane is just for automated vehicles. Of course, another alternative is to separate that lane from the rest of the lanes with barriers to prevent the rest of the vehicles from entering that lane. So this is the general concept. And then once we look at it from the network perspective, again, we might be looking at something like this. So this is not factual or representative of what we have done, but just to show you the concept of how this concept might look like, because having dedicated lanes have been studied intensively with microscopic models on small stretches of roads. But once we look at the problem from a network perspective, and especially if we consider real road networks, things are really very different than they look. And there are a lot of considerations that need to be taken into account. And yeah, in this network, for example, there are many roads that are already a single lane roads, or they have single lane sections there. So it can become quite challenging to think of it from a network perspective and to see, okay, how can we have a proper network of dedicated AV lanes, especially if the idea is that we want them to be connected, because of course you want the vehicles to start manually, enter the network at some point and continue in automated mode, and then at some, once they get close to their destination, they can leave the subnetwork and get to their destination. But then the subnetwork needs to have some level of connectivity. And the next concept is having a network of dedicated AV links, which means longer stretches of roads that are fully dedicated to automated vehicles. The picture on top is the Rivian Park Shuttle in Rotterdam. Many of you are familiar with it. I just selected it as an example of dedicated AV link. In this case, this is a driverless shuttle, which is public transport, not privately owned automated vehicle, but just to demonstrate the concept that this is an example of dedicated AV link. And we can have this kind of links for privately owned passenger vehicles as well. And then again, once we look at it from a network perspective, it can look like this. But again, this is not factual, just an example of how it can look like. And then considering all these three concepts, and AV-ready subnetwork for mixed traffic, dedicated AV lanes, and dedicated AV links, there's another important question here, that which one is the right? There are different studies that have investigated them separately, and the comparison is hard. So far, also, there aren't many studies that have done this on real road networks. The studies are mostly on theoretical networks, and it's really hard to compare them and to know which one is actually the best option. So what we thought was actually maybe the best option is not just one of these. Maybe the best option is a combination of all three. So we tried to formulate a problem and come up with a unified framework for optimizing road networks, considering all these three concepts: AV-ready subnetworks for mixed traffic, dedicated lanes for AVs, and dedicated roads for AVs. And then the question is where and when to deploy these concepts. So what we did was to formulate the problem as a bi-level network design problem, where the upper level represents the decisions to choose which link becomes an AV-ready link, which link becomes dedicated, and includes a dedicated AV lane, and which links will become dedicated AV link. And the objective of the formulation is to maximize total societal benefits, that is optimizing the trade-off between investment cost and deployment of this concept cost, and the benefits they provide in terms of total system travel time and travel time cost. And then the lower level of the problem represents the network equilibrium model with different types of travelers' route choice, which is a multi-class traffic assignment model, where, and the idea is that we represent the interactions between regular vehicles and automated vehicles with differences in PCU values, the capacity changes we consider, and also the differences in value of time. And then we find the equilibrium for the network, and this shows us the propagation of traffic throughout the network. And also, what we did was to consider different types of scenarios with different market penetration levels of automated vehicles, because of what you expect to be a good network for 10% penetration rate scenario is most likely not the best network for 90% penetration rate scenario. So we consider different scenarios to see what will happen under each scenario, and we try to find the optimal design for each scenario based on the formulation I mentioned and the algorithm that we developed. And just a short selection of results here. I'm not going to show you a lot of results, but just to give you a taste of how the results look like. This is the 10% penetration rate scenario, and as you can see here, the purple, or according to MATLAB, magenta color represents the AV-ready subnetworks. And as you can see, the majority of links for 10% market penetration rate scenario for the case study of Amsterdam metropolitan region were selected as AV-ready subnetworks. So this tells us that maybe with lower market penetration rates, mixed traffic is still the best choice. And the next scenario is the 50% market penetration rate, where you can see in this case, there are many dedicated lanes, which are represented with a bright blue or the cyan color. And yeah, as you can see here, in this case, dedicated lanes are more present than AV-ready subnetwork in mixed traffic. And then I want to show you some numbers as well. Just a quick selection. So we looked at the usage of automated driving systems, or ADS usage. We considered different subnetworks for 10% penetration rate, and we look at total travel distance in terms of kilometers, total travel time, and total travel time cost. And just to look at some here, there's an interesting observation that around 70% of the distance driven by all automated vehicles was in autopilot mode, even though we only upgraded 25% of the roads in the whole network. So this tells us actually why it is more efficient to make a good selection of roads, because yeah, if we upgrade all the roads in the network, which will have substantial cost, then we would have 100% of the distance in automated. We could have 100% of the distance in autopilot mode. But what we did was to select 25% of the roads, and we still have 70% of the driving distance in autopilot mode, which is very interesting. And also, once we look at the total travel times, you see that even though 70% of the distance was in automated driving mode, only 41% of the total travel time was in this mode. Of course, this is partly because most of those roads are motorways and high-capacity roads where you can have higher speeds. But still, also when you look at the total travel costs, it's 49%, which is still much lower. And the next thing I want to show is the share of each subnetwork on the optimal designs here. I have different road types, but we'll just focus on all the roads, and I want to compare automated vehicle-ready subnetwork with dedicated AV lanes, which turned out to be the most popular ones or the most efficient ones according to the algorithm. Here, for 10% penetration rate, we have 82% of all roads are selected, 82% of all the feasible roads for deploying this concept were selected for automated vehicle-ready subnetworks, and 17% as dedicated AV lanes. But once we look at the 50% penetration rate scenario, the balance changes. Then we have 42% AV-ready subnetwork and 56% dedicated AV lanes in all the roads. So I specifically selected these numbers to show you just the main conclusions I want to discuss. So in the interest of time, I would move on to main lessons learned. And this is also a selection. If you're interested, there will be an article soon, and also hopefully my thesis will be out soon, so we can see much more details there. But just to share the main lessons learned with you here, the first one is, of course, that large benefits are obtainable by only enhancing a proportion of links or investing on a very small part of the network, which is an interesting finding. As we showed with updating 25% of the links, we can have 70% of the whole travel distance of automated vehicles in autopilot mode. And the next one is that we should always start with mixed traffic first. So enhancing a part of the links for mixed traffic was the most efficient design according to our algorithm and our formulation of the problem, of course. But it showed that with lower market penetration rates of automated vehicles, it's better to start with mixed traffic. And then gradually adding dedicated lanes can have more and more benefits. So this can actually show us a roadmap for the transition period to start with mixed traffic, and gradually, when the market penetration rate of automated vehicles increases, we can add more and more dedicated lanes to realize the most benefits from infrastructure investment costs that we can have. So this is all I wanted to share with you today. And yes, you can, of course, ask me questions, and I'll be happy to share you more details about my presentation and about my work and the rest of the articles. But that is it for today. Thank you.
All right, Bahman, thank you very much. Again, time for one quick question. I don't know if your answer is short as well. There's a question from Dennis Mika, and he asked what the social benefit is of optimizing roads for the private AVs. And shouldn't we focus on optimizing public transport? So it's actually a question of two parts, but maybe you can first address the social benefits of optimizing roads.
Okay, just a quick note that in my thesis, once it comes out in the conclusion section, there will be a long discussion on this. But until then, just shortly, I'll mention that, yeah, one thing is that we have to make a selection of what we want to study, and we studied automated vehicle. In a small part of my thesis, I also considered mode choice and how this can affect other modes and how much induced demand we're looking at from other modes, and that's a different discussion. But here, when I mention the social benefits, it's more in terms of accessibility of certain classes. That in this case, it's more benefits for automated vehicle owners for sure, but also people with regular vehicles can benefit, and the social benefits are also in terms of reducing congestion, reducing emissions that can affect everybody, and reducing travel time and travel time cost for everybody.
All right, thanks a lot. Then it's now time to move on to the third presentation. That's a presentation by Jeroen van der Gun. Jeroen has a background in civil engineering, transport and planning. He already finished his PhD and is now doing a postdoc in the STAD program. So Jeroen, the floor is yours now.
Yeah, thank you, Maaike. I'm Jeroen van der Gun. I work at TU Delft on subproject 6 of the STAD project, which involves the integrated modeling of the spatial and transport impacts of automated driving. And this is, of course, a very broad topic because there are a lot of potential impacts. This picture here is from earlier research by Dimitri Milakis, and you see here that he divided all impacts of automated driving into 3 layers. There are very indirect impacts at the outer layer. For example, you see here public health, economic impacts, air pollution impacts, social equity. If you go further inside, then you see things like infrastructure implications for like road infrastructure and parking infrastructure, vehicle implications, for example, vehicle ownership and sharing, and location and land use implications. But like in the most direct impact layer, so the middle layer here, you see more direct impacts, direct traffic implications, for example, the capacity of a roadway, the amount of congestion, modal split, vehicle use, and travel costs like travel time and other costs paid by or endured by the user. So this is a lot to process, and of course in all these things there is a lot of uncertainty, which makes it difficult to make an integrated model for this. So in my research I am mainly focusing on the inside of this impact model. So mainly starting from what are the direct traffic flow impacts, and in the end then you can from there you can investigate what are then the indirect impacts. But first you need to have the direct impacts modeled. So that leaves a lot of questions. How are we going to model automated driving? And one of the first questions that comes up is, what is the road network? Well, this is actually not a very hard question to answer, because the road network will most likely be very similar to the road network we have now. It won't be completely different, of course. So this is actually, with all the uncertainty that you have about the future, this is actually one of the certainties, and the data, this is part of the data that you do have and that you can use for scenario analysis of automated driving. And this applies both to the road network, but also to the public transport network. It will be different, but it will not be completely dissimilar from the current reality either. And you can certainly make scenarios on what that new network of the future will look like. One of the next questions is like automated driving has a lot of impact on road capacity. So how does road capacity work? Well, capacity is basically the inverse of the minimum headway between 2 cars on the road on the same lane. This minimum headway may of course depend on the vehicle type. So if you're an automated vehicle, it may be different. but also on the vehicle type in front of you. If you have connected vehicles, then you might be able to exchange information, which may change your headway. The vehicle types, of course, that are present on the road depends on the penetration rates of various forms of automated driving. And once you then use that to determine the capacity, and then you have the flow, and you see that the flow exceeds the capacity somewhere, then it means that you will have a queue at that place in the network. The queue will be placed before the bottleneck, and the flow after the bottleneck will be lower because of the traffic that is held back in front of the bottleneck. So here I have a nice poll, and I see that it now already shows the answers from a test run we did before this session. So I have to start the poll again. So you can now vote, I think. I see votes coming in. So in the future with automated vehicles, do we expect capacity in general to be higher or lower? So there are different possible things that might happen. So I am curious what effects you think are dominant. I see people are still voting. Okay, I'll close off the poll because it looks like we have a clear winner already. The majority of you thinks the capacity is going to be higher. And this may actually depend on what types of automated vehicles we get. So if we look at literature, for example, or this literature study also, you see that for autonomous driving, the capacity consumption of a single vehicle is expected to go below 1, and 1 is then the equivalent of a traditional car. So this indeed indicates that the capacity goes up. However, what you see, it might not be certain because, for example, comfort requirements might lead to less aggressive acceleration, which might reduce capacity. So it's a bit uncertain, but the average is indeed expected. On average, it's indeed expected to be beneficial. For cooperative driving, it's different because then it depends on the penetration rate. Because indeed, if there's a vehicle in front of you that you can communicate with, then you can drive more efficiently and more closer to that vehicle in front of you. But of course, it is not simply like one linear road. In reality, you have a network and you also have intersections in that network. And especially in urban areas, it is these intersections that determine the capacity mainly. So for example, here I have a picture of an intersection, and one of the things you see that if you have a capacity constraint, for example, the vehicles that turn left here and the vehicles that go straight here and the vehicles that go left in this direction, they cannot go at the same time. So together, in this case, it's a traffic light, so the green time of this conflict group is limited. If there is but of course, if there is no traffic signals, then the same thing, you have a similar effect that you can still not go drive through each other. With fully automated vehicles, you might actually, there are some proposals for a tile-based reservation system that can magically, seems like magically vehicles can drive all through each other, but then even in that case, a tile can only be reserved by one vehicle at a time. So the total reservation time of a tile cannot exceed the simulation period. In all cases, you also have switching costs. So in a traffic light, there is a time where between one traffic light turning red and the next traffic light turning green. But even without signals, there is a time where you see another vehicle is going to enter the intersection from another direction, so you wait. And you also have to wait until all conflict areas are free so that you can cross the intersection. This approach blocking time might actually reduce if there is connected vehicles that exchange information, because then you have the vehicle can better estimate whether it still fits in. In all cases, you also have that if the intersection is unsignalized, that the yielding arm is at a disadvantage to claiming capacity, which is one of the reasons to signalize junctions. So if we then have looked at the capacity, then the next question is how do the travel times work? So traditionally in research, it is often a BPR function is used, where the speed on the road goes down as the volume goes up relative to the capacity of the road. But while this works fairly well for undersaturated roads, once you exceed the capacity, then this relation does not match queuing theory anymore. So you really want to have another sort of formula here. And in my research, I have worked on deriving a proper formula that indeed places, like I said before, that the queue is placed before the bottleneck, and that you get a waiting time, a queuing time at the bottleneck. And you can derive that from when the vehicles arrive at the bottleneck and depart from the bottleneck. And that depends on the factor of oversaturation, which is here alpha in the formula. But it also depends on the duration of the simulation period, because if the simulation period is longer, then the queue grows longer in that period. And finally, if you have multiple queues in a network, then there is also an interaction effect of subsequent queues along your route, because if traffic is held up in an upstream bottleneck, then the traffic will take more time to arrive at the next bottleneck, and then the next bottleneck also needs more time to process that traffic, which again increases the average queuing time, which is derived from the difference between the surface between the cumulative inflow and cumulative outflow curve. But besides queuing time, you also have simply the waiting time at an intersection. So what I showed previously is deterministic oversaturation delay when the capacity is insufficient. At intersections, there is also a random oversaturation delay, because even if on average the capacity is sufficient, then sometimes you get a group of vehicles arriving and the traffic is temporarily insufficient. So you still get some buildup of queues incidentally. There is also, for traffic lights, there is also obviously a deterministic undersaturation delay. Even if the traffic light is not operating at capacity, then you still have to wait when the traffic light is red. And that still causes you extra travel time, and you can calculate that. And finally, for unsignalized intersection, if you have to yield due to priority rules, then there is a delay because you need to decelerate your vehicle and then look if there is conflicting traffic coming, and then accelerate again when the traffic is clear, when you see that the traffic is clear. So there is a lot of mechanics there. And of course, there's also like how, if you have automated vehicles and you want to have dedicated lanes and roads, how do they work? Well, in terms of capacity and travel time, you have that these dedicated lanes or roads, they have their own separate capacity. They have consequently also their own travel time. If you have a dedicated lane at an intersection, then it can be used to bypass queues. And if there is priority green, for example, which is often used for buses currently, then you can even skip the waiting time at the intersection. So this all have an impact on on the amount of congestion, but also on the travel time of different types of vehicles. Regulations determine which vehicle types are allowed to drive where in this case, but also this may also be due to operational design domain limitations of different vehicle types. And then if there are multiple options possible, then it basically becomes part of the route choice of the user of the vehicle. So how do users make travel choices like route choice? Well, again, you can usually use a utility-based model, which, for example, can include travel time and operation or fuel costs, which are usually tied to distance. The travel time, how that affects it, will depend on the value of time, and that may vary in free flow and congestion, and that may also vary whether you are driving in automated mode or in manual mode. And so the cost of the fuel cost may also vary depending on that. And but besides users with private vehicles choosing their own routes, you may also have public transport that drives on predefined routes. That may also be automated or not. And you could also have routes that are determined by another algorithm. For example, automated taxis. You have a fleet dispatching algorithm that sends taxis to the users that are requesting to make a trip. And that ultimately results in routes for the taxis, and you want to put those taxi vehicle routes into the simulation of the road traffic again. So where does this all lead to if we look at these kinds of things? Well, this has led to me building a model that can be used for scenario analysis with automated driving. This is based on quasi-dynamic traffic assignment based on a road network, which is quasi-dynamic traffic assignment is basically an extension of traditional static traffic assignment, but taking into account explicitly the capacities and the junction modeling. And conversely, it is less complex than dynamic traffic assignment, which requires a lot more data, is a lot slower to calculate. So you can still make good use of the data you have available. You have a solid theoretical basis in queuing theory, including proper modeling of junctions and travel times. And with this way you can make scenario analysis of automated driving, while limiting your risk that you get a wrong outcome because your model is not realistic. So the model tries to use, with a lot of uncertainties in what the future of automated driving looks like, it tries to make the best use possible of the certainties that we do have. And in the future work, because now I've just introduced basically how the model works, and my future work I will also apply the model to case studies assessing the impacts of automated driving in practical scenarios. And there are a variety of possibilities here. For example, I can do comparisons with results from the previous presentations to see how sensitive the outcomes there are to the modeling assumptions, and whether a more detailed modeling of the road network gives you different results. For example, with what bottlenecks are relevant or not, what is the main determinant. And you can also get a more detailed outcome on a local situation in a particular scenario. Something else interesting to investigate is impacts of automated vehicles on bus lanes. Because automated vehicles have typically have a limited operational design domain and may require special infrastructure like Bahman showed in this presentation. It might be interesting to provide that on bus lanes, for example, where there is spare capacity, and see how that affects the road network. Of course, this will all have changes on, for example, intersection geometry, but the model can, in principle, handle this. Something else is what I previously mentioned is, let's say you have an automated taxi system with automated taxis driving around according to a particular strategy. And how will that change travel times in the network, both for the taxis themselves and for the other traffic? And does that change congestion patterns, or where the bottlenecks in the network are? So these are very interesting questions. But since my research, unlike the other STAD projects, which are now mostly ending, is still ongoing, there's also possibility to study other research questions. Particularly, it would be nice to have more master students investigating some of these questions using the model I developed. So if one of you would like to host such a master student as a master thesis internship, then that would be very interesting to collaborate. So I put my email address on the slide here. So if you are interested in applying this model, if you have like, well, I have like this practical scenario that I think would really be suitable for a case study with this model, and I would really be interested in the outcomes, then please contact me with your suggestion. So with that, I would like to thank you for your attention, and well, let's see if there are questions.
Start sharing. Okay, Jeroen, thank you very much. There was the one question that just popped up from Marco. And he says, empty vehicles regrouping or trying to pick up passengers, integrating parcel delivery in a passenger model. That could also be an interesting case. What do you think of that? Is it possible to deal with this in your model?
Yeah, so indeed, so the model basically for like things like automated taxi systems, but also you could also use that for parcel system delivery instead of passengers. You have basically a separate model for, or you can have separate choice models for where the, in that case of a taxi, where the passenger is traveling, like from what origin to what destinations. And then if you have this, for example, origin destination matrix, and then you apply a fleet dispatching algorithm on top, then you can get this to a sequence of routes for individual taxi vehicles. And then on the road network, you can put those taxi vehicles. So that can indeed include empty kilometers, for example. If the taxi drops off a passenger and drives to the next passenger, then this extra trip can be included, or when it is cruising around looking for someone to pick up, then you can also include an extra trips for that. So that can indeed be simulated. And then there's another question, integrating parcel delivery. Yeah, so yeah, if you have basically if you can come up with a choice model that results in or that produces a route for the freight vehicle that delivers the parcels, then you can put that route in the simulation, and then out of the simulation you can get back travel times that you can again feed into the optimization or route choice algorithm, and then iterate until you have equilibrium. So that is, things like that are very possible to analyze with the model.
Okay, sounds good. Also sounds like there's a bit of work to do there. maybe you can say a bit on how much time you have in your research to give an idea of how many questions can still be addressed.
So I have my research still goes until October of next year.
So
yeah, so there is still time.
Might also be an invitation to everybody to ask questions that are relevant for your model. Okay, then I would like to start with the discussion at the end. So Bachtijar and Bahman, can you join the discussion also via webcam?
Yeah, sure.
Yes, I'm here too.
I think that most of the questions in the chat have been addressed, but there's at least one that's not answered yet. Let's see, there was a question from Roxy. I think it was a question to Bahman, and it's about the assumptions of the automated cars.
Okay, I think I missed that one. I tried to find all the questions related to mine.
I noticed it. The question is, it seems that the assumption of this research is that autonomous cars are programmed cars and not self-learning cars. Is that correct?
Oh, we actually we're not considering fully autonomous cars. It's automated vehicles, and we were considering mostly levels 1 to 4, basically. So I excluded level 5 vehicles, which actually could fit the concept as well because they can ride anywhere. But the focus was having vehicles with limited operating design domain. So that means all the vehicles, all the automated vehicles apart from level 5 automated vehicles. But I mean, my reference of discussion is the Society of Automotive Engineers levels of automation. So with Tesla car, I'm not sure what you mean exactly by programmed car, but the vehicles available now, you can consider them level 2 vehicles in this case. So they will be, I think, level 2 automated vehicles. But yeah, if the question is, could they learn from their own experience and improve their performance to be able to drive safely everywhere? I think that's not going to happen with vehicles that are not level 5. And by definition, once we say the operating design domain is limited, it just means that the vehicle cannot handle all situations. So by definition, there are situations that the vehicle can't handle. If it can handle all situations, then by definition, it will be a level 5 vehicle.
Okay. Don't know if that entirely answers the question. I see Roxy is still typing.
Okay.
It's okay, but otherwise we come back to that later. While you're speaking, it might be a nice moment to address the first point on the sheet of Jeroen. He said that it might be interesting to do a comparison with results from previous presentations. So do you think that if you would use Jeroen's model, that you would get completely different outcomes, or do you think it's more or less stable?
Oh, is that question to me?
It's the question to you.
Okay, sorry. I think in general, I would expect to get similar results. I mean, at the end, what I mentioned in my future research directions, which is not here, but in my articles, well, one of the future research directions is actually using either dynamic traffic assignment models or the quasi-dynamic ones, similar to ones that Jeroen uses to model the interactions between automated vehicles and regular vehicles more accurately. But at the end, I expect to get rather similar results. The difference is, I think, what Jeroen's models do and mine don't is to have more resolution and more accuracy around intersections to consider the interactions of automated vehicles and regular vehicles at the intersection, while my models have a very simple node model because I'm looking at a larger network and I need to run optimization models, so there needs to be some simplifications there. So the idea is what my model does is take the average changes that you would expect and we model it with basic simplifications on capacity value of time and PCU value. And this is how we represent the network, but we don't consider the differences in nodes. But Jeroen's model is more accurate in those details of how things will move on intersections and how the queuing will affect, which might change some details, but I don't expect to see fundamental changes in the results.
Okay. It might still be nice.
It might, for example, if you might add it, it might, for example, change. One of the things analyzed is like what dedicated links or like what links should be provided special infrastructure to support automated vehicles. And that might, for example, change if the intersections actually become more important in the model than the links. So yeah, I think I agree that if there is a difference, it will likely have something to do with the intersections and how important the intersections are versus how important the links of the network are.
I agree, certainly.
That's not really the level of detail that Bahman addressed at the moment, so nice for you to check indeed, Jeroen. There's also a question from Baiba. It's to Bahman and Jeroen, but maybe Jeroen, you can take it first. Could you use your models to optimize the route choice for AVs, automated vehicles, and that is to give input to the vehicle manufacturers. For instance, as default suggested routes to optimize flows and minimize congestion.
Yeah, that's an interesting question. So, how the model the basic use of the model is to use user equilibrium routing, which may either be deterministic or stochastic if there are individual route preferences or not. Doing a system optimum assignment is more difficult. In a traditional static assignment based on just BPR functions, this is possible. But in the quasi-dynamic context, the external effects of adding a vehicle to a route, the external effects on the travel time of other vehicles are harder to calculate. There are some studies that have looked into this, but it's quite complex because of the structure of the node models in this. So the intersection modeling, if you have, for example, if you add an extra vehicle, then it's hard to take into account the extra travel time it will cost for all the other vehicles at the intersection. So that is a bit hard. So I guess for Bahman that might be easier because you use BPR functions, right?
Yeah. I think you can with some basic adjustments use. I mean, not exactly model as it is, but I actually considered that scenario and I have codes for it. It's not, as I said, exactly my model, but with some basic adjustments, you can consider system optimal routing. So that's certainly a possibility. But yeah, I think you mean BIBA means system optimal routing, right? Because optimizing the route and to minimize the congestion means optimizing total system travel time, which would mean system optimal routing. But I don't know if that would be useful for vehicle manufacturers actually, because they want to help their customers. So system optimal routing might mean actually that some of their customers might have to be forced to take longer routes to optimize their total travel time and minimize congestion for the whole system. So that's an ongoing discussion there, that it's an opportunity to use automated vehicles, to leverage automated vehicles to do this. But the question is, will the users be happy to have these vehicles that forces them to take the longer route just for the good of the society?
Yes, thank you for your answers. I see that there's a nice remark that a lot of urban transport is missing in all models. So pedestrian, bicycles, mopeds, motorcycles, micro-mobilities. I know it's not completely missing. Bachtijar, can you explain how it's included in the new mobility modeler?
Well, yeah, the modes which are now present in OVIN, so the travel journals, they are included. So that includes bikes as well. And in that sense, it also includes in a new multi-modeler. And we could, in theory, as we did with the automated private car, include a sort of a new type of bike, say the e-bike, or some other modality, which is a micro-modality. But as noted earlier, it's very aggregated at the moment. So we would first need to develop the model further into a more disaggregated state, such that you can also model more disaggregated trips, as these micro-modalities happen on a far more local scale than we currently have. So it is something we will take into account in the future, yes.
Yes, and true interaction at intersections and so on is, I think, definitely interesting, but probably something for future research.
Yeah, for my own model, I can for signalized intersections, I already schedule like some red time because there are pedestrians or bicycles that need to cross. So that limits your maximum. It's part of the conflict group calculation. But detailed modeling is actually quite difficult. For one thing, even if you know the bicycle flows, then it's hard to know on what side of the road, for example, they cross. So that is difficult, but it's not entirely impossible to include that in the intersection modeling.
Okay, and indeed a lot of work to do there also in the future. I don't see any further questions, so I take the liberty to ask one final question to Bachtijar, which is also maybe a nice introduction to the coming webinars. Bachtijar, you mentioned in the beginning that you're trying to include work of also PhD students in the new mobility modeler. Can you very briefly explain what you intend to do there? Maybe for one or two of them is enough.
Yeah. So we talked to quite some PhD students from a STAD program, and we are still looking into how exactly we can implement their work. But for example, BIBA's work would allow us to relate the penetration rate of automated vehicles to the departure time. It would create a small submodel which would determine the departure time based on what penetration rate you set. And we are also, we talked, for example, for Francis Oostermeijer. He looked at the parking rate policy in Amsterdam, and that really gives us a very nice opportunity to validate our model with what he found, to see if the mechanics in our model related to pricing parking are similar to what Francis found. So in that way, we try to implement their work as well in the model.
Okay, thanks a lot. Well, then this is a nice moment to thank you all. It would be nice if I could hand over the flowers that I started with, but that's a bit difficult online. So a short applause in any case for me. Thanks a lot. And I would like to announce the next webinar next week on the 25th of June, same time, so 3 o'clock. And in that webinar, Bahman Madadi, Giulio Macacci, and Francis Oostermeijer will present their work. So everybody is invited to join again. Thanks a lot for joining now and for all your questions. And bye.
Thank you. Thank you.
Thank you. Bye-bye.
Bye-bye.